Hi everyone, my name is Ljunggren. I am a software engineer at NSO Engineering. I joined TLF in 2011 and eventually ended up working for Cisco. Having worked in most parts of the system, I now mostly focus on CDB. Today I'm here to talk about the improvements made in CDB Upgrade for the NSO 6.2 release. I will start to talk about the improved upgrade performance, what has been done, and how the upgrade performance has been improved. At the very start of this project, we made a rough plan consisting of two parts. An initial analysis plan part. The purpose of this part was to implement some kind of schema change analysis in order to establish the minimum amount of work which has to be done in order to fit the old configuration into the new schemas. The second part was a parallelization effort. Once the minimum amount of work has been established, do it as fast as possible. And this effort has not been started. The second point here is improved packages reload action. We have added two new input parameters. And third and not last, we have made several improvements in logging. Logging is not really a first-class feature in itself, but rather a tool to use when something goes wrong, or you need to understand the behavior of CDB upgrade. Before we start talking about CDB upgrade, let's talk about two related operations that are different from CDB upgrade in that they are limited in what they change and they don't affect running services. The first operation is the simplest of the three. The packages add action loads one or more NAID schemas, NAID packages, and extends the schemas. Running services are not affected. The second operation is the migrate action, which upgrades a subset of the configuration, one or more device configs, from one device model to another device model. Both device models must be part of the schemas when the action is invoked. The schemas are unchanged and hence running services are not affected. This partial type of upgrade is possible only because of the mount points, which make it possible to load several versions of the same namespace at the same time. Last but not least, CDB upgrade. CDB upgrade can be triggered automatically during start of NSO or invoked as an action, the packages reload action. This operation permits arbitrary modifications to the schema. As you can see in the upper right corner, the schemas are changed by adding, deleting, or modifying namespaces. Since any part of the schema might be affected, running transactions are not allowed and must be stopped. This is done by starting an upgrade server, orchestrating the upgrade, making sure to stop all running transactions before loading new schemas, etc. When the new schemas have been loaded, the old contents of CDB must be converted to fit into the new schema. This requires work to be done by CDB, more specifically upgrade work. Upgrade work is something that has to be done to make a value or a node in the old config fit the new schema. The individual upgrade work items may be simple, as a data type change for a leaf, or very complicated. For example, changes in a nested choice case structure. Most types of upgrade work are directly caused by changes in the YANG module. For example, change of a data type. There is also upgrade work caused by indirect changes in the YANG modules due to non-local dependencies. And examples of non-local dependencies are found in must and when statements, instance identifiers, and identity refs. Instance identifiers are problematic since they are untyped. They correspond more or less to a void pointer in C. There are no clues about what schema node they refer to. If the upgrade deletes any node in the configuration, all occurrences of instance identifiers has to be checked for validity, unless of course require instant false is used for the node. As the YANG language is very expressive, there exist many types of upgrade work, and some of them are fairly complicated. Here is a list of examples of upgrade work. Here are 4 simple examples of YANG changes and whether or not they cause upgrade work. The first one does not result in upgrade work, since the data type is widened, and hence all existing config values fit into the new schema. The second one is the opposite of the first one. Here we go from an unsigned 32 bits to an unsigned 16 bits. And this requires upgrade work since all the values in the old configuration has to be checked. The third one changes the node type from container to list, which of course implies upgrade work. And finally, the fourth example with a relaxed validation constraint, which means no work is necessary. Here is a basic outline of the upgrade sequence once decision is taken to actually upgrade. We start with the prelude, setting everything up for the later phases. The prelude includes making sure both versions of the schemas, the old and the new one, are accessible, and creating an upgrade transaction, which serves as a destination for all changes made to the config. Next comes the perform upgrade, where the old config is traversed, making changes to the upgrade transaction according to the schema changes. Nodes deleted from the schema are handled separately. Finally, in the postload, the result is made persistent, assuming the transaction apply is successful. While traversing the config, a schema change cache is gradually created. At no time a complete picture of the schema changes is available. Sometimes the cache is available, sometimes not. So it's all good? No, we have a problem. Upgrades with minor changes to the schemas sometimes suffer from long upgrade times, and this should be improved. Making major changes to the schemas may continue to take time. Rewriting parts of the config cannot be eliminated. So why does minor changes to the schema sometimes result in long upgrade times? There is no proper and thorough analysis of the schema changes. Instead, this schema change cache is gradually created as the config is traversed. This cache is sometimes not enough to avoid unnecessary searches for new validation constraints, etc. Also, the cache is not used in all parts of the upgrade code. To conclude, efficient pruning is needed in order to avoid unnecessary traverse of the config. The second explanation is that validation constraints of type must expressions are always triggered for re-evaluation. This causes the change set to grow, and more importantly, the final apply of the upgrade transaction to get more validation work, much more validation work. Limit the traversal. Let's look how the configuration is made to fit the new schemas. The configuration essentially consists of a number of trees, one for every namespace. Now we have to make sure every one of them fits into the new schema. But only the parts of the configuration that has upgrade work associated with them have to be traversed. If we had access to the upgrade work items like a change set, we could use it to guide the traversal and only visit parts of the configuration that needs work. Upgrade tree, a tree of upgrade items. The idea is to keep all upgrade work items in a tree, similar in structure to the old schemas. By doing this, the paths used when traversing the old configuration may be used to look up upgrade work items. The upgrade tree has the following property. A node exists in the upgrade tree if and only if there is upgrade work at or below the current node. An important corollary is that if no node exists in for the path in the upgrade tree, there is no upgrade work below. This is the basis for pruning. The path used for traversing the old config is used to decide whether to prune or not. How would such a tree look? Before looking at an upgrade tree, let's start with a simplified picture. In the example above, the schema has been modified in such a way that upgrade work exists for the D schema subtree. B and C subtree do not have any upgrade work. A corresponding upgrade tree, which you can see on the right, will only have nodes in the D subtree. Lookups for any node in the B or C subtrees will return nothing, indicating that pruning should be done. Here's an actual example of an upgrade tree. On the left you will find two versions of a simple Young module. Nodes have been added, modified, and deleted. On the right hand is the corresponding upgrade tree, really an excerpt from the upgrade log. Some nodes have no flags at all and exist just because there is upgrade work below. I will not go into the details here, it's left as an exercise to the viewer. Here is an outline of the new upgrade sequence. A new schema analysis stage is inserted just before the perform upgrade stage. The goal is to improve the analysis of the schema changes, thereby reducing the amount of upgrade work and use pruning more effectively. In addition, there are other benefits of separating the two stages. One obvious example is improved testability, for example. And it's also easier to implement dry run-like functionality. The slogan here is, by investing more in the first stage, a higher return on investment is possible in subsequent stages. What's the output of the schema analysis stage? Upgrade and schema diff trees. An upgrade tree will contain all upgrade work that needs to be done in order to convert the old config to the new schemas. It is structurally similar to the old schemas and with some nodes added from the new schemas. So it's really a kind of a union of old and new schemas. And then there is the schema diff tree, which has a different purpose, to generate an upgrade report. This is just some short notes about upgrade trees, how they are built. So information is propagated from the bottom to the top, just like a Merkle tree. Initially, Merkle trees were used as an intermediate step, but dropped as we realized they provide no extra value. The end result will be a tree containing the minimum amount of upgrade work. Global dependencies found in must and when statements must be handled separately. We use dependency information provided by the compiler and loader. In addition to upgrade trees, the schema diff tree is also generated. Whilst the purpose of the upgrade tree is to guide CDB internally, the purpose of the schema diff tree is to generate upgrade reports for the user. So why is this distinction important? As an example, changing a non-presence container to a presence container is not visible in the upgrade tree, since there is no upgrade work associated with the change. As a service programmer, on the other hand, it is important since the presence container has to be explicitly created. Upgrade and schema diff trees are an internal concept, visibly only in the upgrade log. Let's talk about something more tangible, the packages reload action. We have added an input parameter for generation of upgrade reports. Initially, only schema changes are supported. The modified path structure is identical to the one used in the NED migrate action. Service-related metadata is initially not supported, but it's a candidate for future releases. We have also added an input parameter called dry run. The upgrade will be aborted and no changes will be made towards the schemas or configuration. Please note that this parameter still impacts running services or transactions have to be stopped. This parameter is typically used combined with the report parameter. Logging. There are lots of changes when it comes to logging. First of all, CDB now logs everything related to upgrade in a separate upgrade log. The upgrade log is configured as any other log in ncs.conf. The upgrade and schema diff trees will be printed in the upgrade log. And we will also print something called upgrade event counters. CDB maintains a set of counters, one for each type of upgrade work. And whenever upgrade work is performed on a config node, the corresponding counter will be incremented. The upgrade event counters provide feedback on the amount of work done without flooding the upgrade log with excessive information about each and every instance. Here you can see an excerpt from the upgrade log with parts of the upgrade tree for the running database. And the final part of an upgrade with the upgrade event counters. And finally, some preliminary results. We have been using a test case for the core function pack suite. The core function pack extends the NSO core platform to address specific use cases. So it's an add-on on top of NSO. It's a very complex when it comes to the number of packages used. You can see here 20K number of services, 6,000 devices, fairly big configuration, and a very big schema. So here is a result. The core function pack test it's interesting because it has many namespaces, and so it's a complex schema. And we can see around 5 times speed up in this specific test. I think we have better figures now. Why faster? There are several factors for the performance improvement. The first one is more efficient pruning of the config traversal. It's the upgrade tree, which is minimal in terms of upgrade work. The second explanation is dependency-based triggering of validation constraints. We no longer always have to reevaluate must statements, and that's very important. And the third explanation is improved validation in the transaction engine, which is not part of this project, but it was included in the 6.2 release. Future. What does the future hold for upgrade operations? We have just started to work on the parallelization parts of the upgrade code, building of upgrade trees is already utilizing all available cores. Since no transactions are allowed during CDB upgrade, it makes sense to use all available cores. Adding service-related metadata to upgrade report. We would like to bring the improvements done in this project to the net migration. So we will switch from using Merkle trees to using upgrade trees. And finally, extend packages add to accept standard packages as well. Okay, thanks for listening.